Alright, today we're going to cover the Physics Paper 2. This is the extended multiple choice paper, so it's the 0625/22 code, and this is for October-November 2018. This is of course the Cambridge IGCSE, so this is from the Cambridge International Examinations, CIE. Alright then, let's begin.
Let's go! Let's go!
Question 1. The diagram shows part of a micrometer screw gauge. What is the smallest reading that can be achieved using this micrometer screw gauge? Alright, well, a micrometer screw gauge will read 1/100th of a millimeter. So there we go, that's option B. Question 2. The speed time graph shows the motion of a car. At which time is the acceleration the greatest? Alright, well, acceleration is change in speed over change in time. Technically, it's change in velocity over change in time, but you'll find they do this a lot in exam papers where they just conflate the two of them. Alright, so here we go then. Nonetheless, change in speed divided by change in time. Now, what we're looking for is a point on the graph where the gradient, because this is a gradient, is the biggest. So what we're looking for is a bit in the graph where the gradient is the steepest, and that's along this section here. So that is B. 3. An athlete runs at a speed of 8 meters per second for 10 seconds, and then at a speed of 6 meters per second for 12 seconds. Which calculation gives the average speed of the athlete in meters per second? Now, we want to be a bit careful with this because the average speed is given by the total distance divided by the total time. Now we know that speed equals distance over time. And from that we get distance equals speed times time. So if we look at it, we've got two parts that are of interest. We want distance 1 and distance 2. So the total distance is given by 8 meters per second times 10 seconds plus 6 meters per second times 12 seconds. That's the total distance. Now the total time, of course, we're given is just going to be 10 seconds plus 12 seconds. There we go. So that gives us 8 times 10 plus 6 times 12 on top, and on bottom we'll have 22 seconds. So that then is answer B. Question 4. A helium balloon is tied to a top pan balance. A metal block of mass 100 grams is placed on the balance. The reading on the balance is 91 grams. Okay, so the balloon is pulling up with a force which changes the reading on the balance. So let's look at the statements that could be correct. A. The balloon exerts a downward force of 0.09 newtons. Nope, it's an upward force. B. The helium has a mass of -9 grams. No, you don't have any negative masses. It has a mass of +9 grams. Nope, it doesn't have that either. Right. D. The resultant downward force on the top pan balance is 0.91 newtons. Well, let's see. We have here the resultant mass, if you like, that is reading. Now let's convert that into a force. We know that weight equals mass times gravity. We want to find the weight. So the weight will be 0.091 kilograms multiplied by 10 meters per second squared, which will give us 0.91 newtons. So excellent. That looks correct. The answer is D. 5. The diagram shows 4 metal blocks of different metals. Each block has a mass of 12 grams. Which metal has the largest density? Okay, let's look at what we know. We know that density is mass divided by volume. They've all got the same mass. I want to find which one has the biggest density. So I'll be looking for the one which has the smallest volume. So we're going to look through them all and find out which one has the smallest volume. The volume for A is going to be 1 centimeter times 1 centimeter times 2 centimeters, which is 2 centimeters cubed. For C, it's going to be 1 times 1 times 3, which is 3 centimeters cubed. For B, it's going to be 1 times 2 times 2, which is 4 centimeters cubed. And for D, it's going to be 1 times 2 times 3, which is 6 centimeters cubed. So the one with the smallest volume and therefore the largest density is A. 6. The graph shows how the length of a spring changes when a stretching force is increased. In the Hooke's law region, what is the spring constant for this spring? Alright, so Hooke's law region is this bit along here where we've got this nice straight line. So let's put down Hooke's law. F equals kx. We're being asked to find spring constant k. So k equals F over x. Now, we've got a graph here, so we're going to be putting in our change in force divided by the change in extension. Okay, now we've got a nice little section here where it goes through a beautiful easy to read line, a beautiful easy to read line down at the start there. So our change in force is just 5 newtons, and our change in extension is 20 minus 5 centimeters. That's 15 centimeters. So that's 5 newtons divided by 15 centimeters, which is 0.33 newtons per centimeter. There we are, and that is option D. Question 7. Point X is the centre of mass of a lamina in the shape of a triangle with sides of equal length. The top of the triangle is cut off along the dotted line shown. What happens to the centre of mass X? Right, the centre of mass is a point where if I wanted to, I could put something underneath and balance it on that point, in this case while it was lying flat. Now that means that all the forces on this side would balance all the forces, the turning forces on that side. Now if I take off this bit up the top, then what I'm effectively doing is taking off a bunch of the forces. So suddenly this side would push down more and it would flip up, which means our centre of mass is actually moved further down the page. There we are. So that answer then is A, moves towards the bottom of the page. Question 8. An object of mass 3 kilograms travelling at a speed of 6 meters per second collides with an object of mass 2 kilograms travelling in the opposite direction at a speed of 2 meters per second. The objects stick together during the collision. What is the speed and direction of the combined mass after the collision? Okay, so what we're going to use here is our conservation of momentum. The momentum at the start is going to be equal to the momentum at the end, and that's always true, but the total momentum. So we're going to look at the momentum of each object individually. We're going to add that together, and that will give us the initial momentum, and that will be the same value as the momentum at the end after the collision, when the two masses have combined. So momentum is mass times velocity. Now, if we look at the section on the left, it's coming in at 6 meters per second. It's got a mass of 3 kilograms. The momentum of that object will be 6 meters per second multiplied by 3 kilograms. It will be 18 Newton seconds. And on the right hand side, we have an object going to the left. Its speed is 2 meters per second. It has a mass of 2 kilograms. So mass times velocity is 2 times 2. That's 4 Newton seconds travelling the opposite direction. Our resultant momentum would be 14 Newton seconds travelling to the right. Okay, so let's look at that. Momentum is mass times velocity. I want to find the velocity of our final object. Well, momentum before equals momentum after. The initial momentum is 14 Newton seconds. The final momentum is also 14 Newton seconds. And again, that equals mass times velocity. So we have the mass, which is now the two objects stuck together. That's 3 kilograms plus 2 kilograms. And multiplied by the velocity that we do not know. So the velocity will just be 14 Newton seconds divided by 5 kilograms, which gives us a value of 2.8 meters per second. There we go. And that is travelling to the right, so the answer is D. There we are. 9. Which device is designed to convert chemical energy into kinetic energy? Alright, so chemical energy into kinetic energy. Well, what starts with chemical energy? An AC generator? No, it starts with motion. Battery powered torch starts with chemical, doesn't end up with kinetic, it ends up with light. A car engine, well, we start off with petrol, that's chemical, and it makes it turn as it explodes, so yeah, that's kinetic, that's a good possibility. Wind up mechanical clock? No, we start off with that potential energy from the spring, which becomes kinetic. So no, the answer is C, a car engine. 10. The diagram shows a pendulum. The pendulum swings from P to Q to R and back to P. P is 10 centimeters higher than Q. Alright, excellent. At what speed does the pendulum bob pass through Q? Now, there are two equations that are important here, and let's look at what's actually happening in terms of this change of energy state. We start off with gravitational potential energy when it's at its highest. That changes into kinetic energy as it travels to its lowest, and then back to gravitational potential energy when it gets to the highest point on the other side. So what does that mean? Well, let's pull out our equations. We have mass times gravity times height is going to be equal to the kinetic energy when it's at its lowest point. So the potential energy at the highest point will be equal to the kinetic energy at the lowest point, which is 1/2 mv squared. Looking at those two, I can cancel the mass on either side, and that'll give me GH equals 1/2 v squared, and I can rearrange that to get the velocity. The velocity will be given by the square root of 2gh. Okay, so let's put that in. That's the square root of 2 times 10 meters per second squared multiplied by 10 centimeters. That's 0.1 meters. Excellent. And that gives us a value of 1.414 meters per second, which is option C. There we are. Question 11. A crane on a building site lifts bricks of total mass 200 kilograms, initially on the ground, with a uniform acceleration. When the bricks are 5 meters from the ground, they have a speed of 5 meters per second. How much work is done during this process? Okay, two things are happening. One, the bricks are going upwards, so you've got a change in the gravitational potential energy. And the second thing that's happening is the speed is increasing, which means you have a change in the kinetic energy. So the total work done will be equal to the change in gravitational potential energy plus the change in kinetic energy. So let's put the numbers in and find out what that actually is going to give us. Okay, so gravitational potential energy, we have mass times gravity times height, which is 200 kilograms, times gravity, that's 10 meters per second squared, times height, which is 5 meters, plus our change in kinetic energy, which is 1/2 mv squared, 1/2 times 200 kilograms, times v squared, which is 5 meters per second squared. Excellent. And if I put all that information in, then I'm going to get a value of 12,500 joules, or 12.5 kilojoules. Excellent. And that is option C. 12. A manometer is used to measure the pressure of a gas supply. Which change gives a greater value of the height h? Alright, well, first things first, let's look at what this actually represents. The difference in pressure is equal to density times gravity times height of the liquid, and the height is the height difference here. So we're being asked really, how can we make this value of the height difference bigger? Probably not by changing the pressure of the gas supply. So we're just looking at things we could change. Now looking at that, I'd say probably it would be make the density smaller for the same pressure change. In fact, there we go, that's one of our options. The first one, A, use a less dense liquid. A more dense liquid would make a smaller value of H. A narrower tube doesn't actually have any effect, and neither does a wider tube. So the answer is A. Question 13. A wash basin has an exit pipe covered with a plug of area 12 centimeters squared. A chain is attached to the center of the plug to assist in pulling the plug away from the exit hole. The wash basin contains water to a depth of 0.8 meters, or 0.08 meters. The density of water is 1,000 kilograms per meter cubed. What is the force acting on a plug due to the water? Well, first things first, let's find the pressure at the bottom of that sink. Here we go. Pressure is density times gravity times height. So here we go, it's 1,000 kilograms per meter cubed times gravity, which is 10 meters per second squared, times the height, which is 0.08 meters. There we are. And that gives us a value of 800 pascals. Alright, now what we do now is we know that pressure is force over area. We're going to rearrange that so that force equals pressure times area. We want to calculate the force. So the force is pressure, 800 pascals, multiplied by the area. Now the area here is 12 centimetres squared. But there's a key point that becomes very important. The area, when we're working with pressure, should really be given in metres squared. So what does that mean? Well, if I've got centimetres squared here, I know that a metre is 100 centimetres by 100 centimetres. So to convert centimetres squared to metres squared, I need to divide it by 10,000. So if I put that information into the calculator, that will give me a value of 0.96 newtons. And the answer is option A. There we are. Question 14. Diagram 1 shows the apparatus being used to observe smoke particles. Diagram 2 shows how a smoke particle moves randomly. Okay. Why do the smoke particles move randomly? Well, they're moving randomly because they're being hit by all these little molecules of air that are flying down in random directions and are colliding with them in random ways and knocking them about a little bit. So, A, they are hit by air molecules, yes. They're less dense in air? Nope. Moved by convection currents? Nope. And they gain energy from the light? No. The reason I put no for the moved by convection currents, because obviously they would be, is that this is quite a small box. So there's not a lot of movement going to happen there because of convection currents. So it's all controlled by the air molecules. So the answer is A. Question 15. A closed container of gas is heated. The pressure of the gas increases. Which statement explains this increase in pressure? Alright, well, as the temperature goes up, the random kinetic energy of the molecules go up, and they're starting to hit the sides of the container, the walls of the container, harder and with more force, and the change of momentum that they experience is greater. So the force on the inside surface of the container will also increase. The pressure increases because pressure is force over area. So A, the changes in the momentum of the molecules striking the walls of the container increase. Yep, that's true. The change in momentum is bigger. B, the force of attraction between gas molecules and the wall increase. Nope. The gas molecules collide with each other more frequently. Wouldn't affect the pressure of the actual container walls. D, the gas molecules lose more energy when they strike the walls of the container. No. So the answer is A. Question 16. The metal lid on a glass jar is difficult to unscrew. The jar is placed in a warm oven until the jar and the lid reach the same temperature. The lid is now easily unscrewed. What property accounts for this? Alright, let's look through the options. Thermal capacity of the jar, that's just to do with how much energy it takes to heat it up. The lid, we don't really care about that. Thermal conduction, nope, how well it conducts heat through the jar. And thermal expansion. The lid will expand a different amount to the glass jar. So the answer is D. Question 17. A block of iron of mass m is heated and gains 10 kilojoules of internal energy. The temperature of the block rises by theta degrees Celsius. A second block of iron of mass 2m is heated and gains 5 kilojoules of internal energy. What is the temperature rise of the second block in degrees Celsius? Alright, well, let's look at the equation that governs this. We know that E equals mc delta T. And we know that delta T is given by the energy supply divided by mass times specific heat capacity. That's just rearranging that. So for our initial amount, we have 10 kilojoules of energy in, and we have m times c at the bottom, the mass, times the specific heat capacity at the bottom. So this is delta T1. Now let's look at delta T2 and see how it relates. What do we have? Well, we've got 5 kilojoules of internal energy. So that's 5 kilojoules divided by the mass is doubled, 2m, and the specific heat capacity is the same. Alright. Well, let's look at how this relates to the original number. 5 kilojoules is 1/2 of 10 kilojoules. So that's a half times 10 kilojoules divided by 2mc. If we look at that a little bit more, what we can see is that's really the same as 1/4 times 10 kilojoules divided by mc, which is That's the original value here for delta T1. So that means it's 1/4 of the original value. So there we are. The answer is A, theta divided by 4. Question 18. Which factors affect the sensitivity of a thermometer? Number 1, the diameter of the bore of the tube. Yep, you'll see much bigger changes for the same amount of temperature change if the diameter of the tube changes, especially if it gets small. You'll see much larger change. If it gets wider, you'll see much smaller changes. The length of the tube does not affect it at all. And the thickness of the bulb wall, well, I guess in this case we're just assuming it goes in and there's no time limit to it to change to the actual temperature, so that's not really going to affect it either. If there was a time component in there, if it needed to change temperature quickly, then obviously that would affect it, but otherwise you just put it into this enormous reservoir of material that you're measuring the temperature of and wait. So the thickness of it just means you have to wait longer to get a good, solid, accurate reading there. So, A, the diameter of the bore of the tube will be the thing that has the greatest effect for the sensitivity of a thermometer. Question 19. Which statement about convection is not correct? A, it enables water in a pan on a cooker to get evenly heated. That's true. You get convection currents inside a liquid. B, it happens in liquids and gases. Absolutely true. You get convection currents occurring in those two things, just not solids. C, it means that heat rises. No. Convection does not cause heat to rise. Heat rises, causing convection. So it's a little bit of an odd, putting quite a fine line between the definitions there. So convection doesn't mean that heat rises. Heat rising causes convection. So no. And of course that happens because of the change of density in the liquid or the gas. D, it occurs because the density of a fluid decreases when it is heated. Well, that's absolutely true as well, as we just mentioned. Okay, so the thing that is not correct, that is not true, is C. There we go. Question number 20. A lamp has a metal filament that glows when heated by an electric current. The middle of the filament is at a very high temperature. The ends of the filament, which are connected to the base of the lamp, are cooler. Which statement is correct? Okay, let's look through our statements. A, some thermal energy is conducted to the base of the lamp. Oh, yeah. A little bit of thermal energy will be conducted off to the base of the lamp, so that's right. B, the filament radiates energy equally in all points along its length. No. I'll show you why. Because it just told us, there we go, here we got a filament for the lamp, like so. It told us it's going to be hottest here, so it's going to give out the most energy at this point. And if it's colder towards the end, then it will give out less energy towards the ends. There we go. So it's definitely not that one. C, the lamp transfers all of the electrical energy it receives into light energy. No, because it also gets hotter and transfers some heat through to the base of the lamp. And D, when the voltage across the filament is halved, the power output is halved. No, that's not correct either. I'll show you why. We'll assume that the resistance is constant. It's not a good idea, but it gives us a good rough estimate section that we can work with. So V equals IR. Let's assume that R is constant. If we end up with V divided by 2, then we end up with I divided by 2. Okay, that's fine, but let's look at power. Power equals I squared R. So we'd then end up with the power for our second setup, if you like, would be I divided by 2 squared times R, which would actually give us IR divided by 4. So it would actually give us IR divided by 4, which is a quarter of the power output. So it is definitely not D either. And the answer, there we go, is A. 21. Plane water waves travel from a shallow region into a deeper region. They travel more quickly in the deeper water. Which diagram shows the wave patterns in the deeper water? Well, let's look at this. Let's just see what's happening here. Okay, so the moment they get into the deeper water, they speed up, which means they'll start accelerating away. They'll be travelling faster than the water which is still in the shallow section. There we are. We should end up with a pattern that looks a bit like that because they're travelling faster. Alright, which to me looks like option C. Question 22. A thin converging lens has a focal length of 6 centimeters. An observer looks through the lens at an object which is placed 4 centimeters from the lens. Which description that is observed is correct? Okay, let's pause for a second here. Let's just see what's happening. So it's got a focal length of 6 centimeters and it's placed 4 centimeters. Okay, so the focal point would be actually behind it here. And at that point, what's going to happen is it's going to create a virtual image, and it will be larger, just like using a magnifying glass. Alright, so here we go. It's going to be option D, enlarged in virtual. Question number 23. A transmitter produces radio waves of wavelength 1500 meters. It takes the waves at 0.025 seconds to travel from the transmitter to a radio receiver. What is the distance between the radio transmitter and the receiver? Okay, so there we go. We've got the wavelength. We've got the time it takes. And we have to find some way, we have to find the distance between the radio transmitter and the receiver. Well, something that's important here is this number there is a red herring. It is just designed to make us think we need to use it. We do not. Speed is distance divided by time, which means that distance is speed times time. Now, when we're dealing with a radio wave in air, travels at the speed of light, 3 times 10 to the power of 8 meters per second. And the time it travels for, 0.025 seconds. There we go. If we put that information in, we will get 7.5 times 10 to the 6 meters. Question 24. Different parts of the electromagnetic spectrum are used for different purposes. Below are 4 statements about parts of the spectrum. Statement 1. Infrared waves are used in television remote controllers. That's true. 2. Radio waves are used to transmit television pictures from satellite to Earth. No. 3. UV waves are used for intruder alarms. No. And 4. X-rays are used for security checks. Well, that's absolutely true. There we go. Alright, so that gives us statement 1, statement 4 are correct. And the question, which statements are correct? Well, 1 and 4. There we go. Question 25. A sheet of ice floats on water. A source of sound, S, is positioned at the edge of the ice sheet. 4 microphones are placed equal distances from S. Which microphone detects the sound from S first? Alright, well, let's look at the speed of sound. Speed of sound in air, well, that's about 340 meters per second. Speed of sound in a liquid, give or take, that's about 1 kilometer a second. And speed of sound in the solid is about 5 kilometers a second. Which means we'd expect the sound to be heard fastest by the microphone, which is attached to the same solid where the sound is being produced. B. Question 26. The diagram shows a bar magnet at rest on a smooth horizontal surface. A length of soft iron wire is held parallel to the magnet. The wire is released. What happens? Well, straight away we know that the iron is going to be attracted to the magnet. So let's look at our options. The wire moves away from the magnet? Nope. The wire moves towards the magnet. Well, that's absolutely going to happen. C. The wire stays in its present position and rotates for no reason whatsoever. It stays in its present position and rotates the other way. No, not that one. So the answer is B. It goes towards it because of the induced magnetism. Question 27. The diagram shows point X between 2 charged plates. Which diagram shows the electric field pattern near point X? Okay, well, let's just talk briefly about electric fields while we're here. Okay, we've got all these field lines coming in like this, from one side to the other. When you get to the end, of course, they bulge out slightly. That's fine, that's the edge effect. Which is why they've chosen a point in the middle to ask questions about. Now, whenever we draw field lines, we draw them as travelling from positive to negative, like so, for electric fields. There we are. Which means the answer we'd expect for the electric field pattern is A. Question 28. A bar magnet is placed inside a current carrying coil. The diagram shows 4 different experiments. One, magnet removed slowly. Oh, here we go. Yeah, I can see what's being changed. We've got the magnet removed slowly and the current being reduced. Here we've got AC and here we've got DC. And same at the bottom. Over on this side we've got AC. Over on this side we've got DC. Okay. So the top section, the magnet's being slowly removed. In the bottom section, the current in the coil is slowly reduced. In which experiment is the magnet demagnetized? Right, let's look at that. So, if we look at 1, it would be demagnetized. That's a recognized way of getting rid of magnetism. 2, it would not be demagnetized because the current's always travelling in the same direction, so it would just maintain its magnetism based around this external magnetic field from the wire. Okay. 3, yep, that would work. We've got this alternating magnetic field inside and slowly being reduced, same as section 1. And 4, we've got DC, so DC would not work for the same reason as 2. The magnetism isn't being changed at all, so it will just stay as good as it was, I guess. Which gives me 1 and 3. So it's demagnetized in 1 and 3, which is option B. Question 29. Copper wire is available in fixed lengths, but in various diameters D. Each diameter has a different resistance, R. Which relationship between R and D is correct? Okay, so let's take us to the very start. Resistance is proportional to length over area. Alright, now area is proportional to the diameter squared, which means that resistance is proportional to L over D squared. So resistance is proportional to the length, and it's also proportional, or inversely proportional, to the diameter squared. There we go. So let's look for which one says that. R is directly proportional. No, it's not. It's not directly proportional at all. Inversely proportional to D? No. Inversely proportional to D squared? Yes. It's option D. Question 30. A student investigates the resistance of a lamp. Which row states how the meters must be connected? Okay, we're connecting an ammeter and a voltmeter. So a voltmeter is always placed in parallel, and an ammeter is in series. So a voltmeter in parallel, and the ammeter is placed in series. There we go. So it's option C. Question 31. The circuit shown is used to change the voltage V out as the temperature of device X changes. Which row is correct? Well, if device X changes its resistance with the temperature, then it's going to be some type of thermistor. Here we go, so thermistor here and thermistor here. Now, we're taking some voltage across the circuit, the midpoint of the circuit there. What we're doing is dividing the potential difference being provided by the battery up the top. So in that case, this is a potential divider circuit. Here we go. It's B. So we're using some fraction, a changing fraction of the voltage that's provided. That's a potential divider circuit. Question 32. The circuit diagram shows a DC power supply connected to 2 resistors R1 and R2 and 4 diodes. Which statement is correct? Okay, current R1 and R2, current in R1 but not R2, current in R1, not R1 but current in R2, and no current in R1 and no current in R2. Well, let's look at it. Let's see what's happening. It's a DC power supply, so we just follow it round in one direction. It's not changing, so we don't worry about it coming backwards. Travels up here, travels up here, travels up here, travels up this bit, cannot go down to the right, so it's going to come down here, travels up there, travels down and along and back. Okay, so that's good. It's going to work, and you're going to get a current in R1 and a current in R2. So there we go. The answer is A. Question 33. A logic gate has inputs 0, 0 and an output 1. Which 2 types of logic gate behave in this way? Alright, let's see, we've got 0, 0 and output 1, and the question is what mystery thing lies here? Well, an OR gate would take a 0 and a 0 and return a 0. So that means that a NOR gate, and I'm not drawing the symbols on at this point, would take a 0 and 0 and return a 1 because it's the opposite of an OR gate. Now, an AND gate would take a 0, 0 and return a 0, which means a NAND gate would take a 0, 0 and return a 1. So a NOR and a NAND would do the job, which is option D. Question 34. Either a fuse or a circuit breaker can be used to protect electrical cables from large currents that could cause overheating. When a fuse is used, where should it be connected? And when a circuit breaker is used, where should it be connected? Alright, well, both of them should be connected in the live wire as early as possible. So protecting electrical cables from large currents that could cause overheating, we're going to want them outside the appliance here. So we'd really want them at point X. And that'd be the same for both the fuse and the circuit breaker. So there we go. Our answer is A. Question 35. Electrical power is transmitted at 400,000 volts and transformed down to 240 volts before being delivered to consumers. Which statement is correct? A 400 kilovolt cable requires less insulation? No, requires more voltage. B. Birds are subject to high voltage shock when resting on a high voltage cable? Nope, not at all. They're attached to the same voltage. There's no massive reduction that could happen there. C. The current of transmission wires is equal to the current delivered to the consumers? It is not. And D. With a 400 kilovolt system, the small proportion of energy is used to heat the atmosphere than with a 240 volt system. Yeah, what it's saying there is less energy is lost to heat. D. They've just decided to word it in terms of the atmosphere. But that's what happens. You heat the wires heat the atmosphere. Question 36. The diagram shows a coil of wire between the poles of a magnet. The coils consist of 20 tons of insulated wire. The coil is connected to a variable resistor and a power supply. How can the turning effect on the coil be increased? Okay, well, there's a couple of ways we can increase the turning effect. We can increase the number of turns. We could increase the strength of the magnetic field, or we could increase the current. So let's see. By moving the poles of the magnet closer together, well, closer to the coil, yeah, that would actually increase the magnetic field strength at that point. By reducing the number of turns of coil while keeping the current constant, no. By increasing the resistance of the variable resistor, well, that will decrease the current. And D, by reversing the terminals of the power supply, that would make zero difference whatsoever, just turn it in a different direction. Ah, there we go. There are options in, so that's just option A. Question 37. Which diagram represents the structure of a neutral atom? Alright, we want the same number of electrical charges outside, negative, as there are positive charges inside, so it's not A. B's got 2 outside, 2 inside, that would work. C's got 2, no, it's not C, not D. There we go, so the answer is B. 38. A radioactive nucleus, 22086 from radon, decays in 2 stages to produce lead, Pb, which is 212 and 82. Which 2 particles are emitted in this process? Now, if we look at it, we can see we've lost 4 protons and 8 protons plus neutrons. Now what that means is we've lost 2 alpha particles, because an alpha has 4 protons and neutrons and 2 protons. So there we go. All that's happened here is our radon nucleus has decayed twice through 2 alpha decays to produce lead. And that is option C, 2 alpha particles. 39. The diagram shows the paths of 3 different types of radiation, X, Y and Z. Which row correctly identifies X, Y and Z? Well, Y stops straight away. First thing it hits, which is a tiny bit of plastic, it's going to be an alpha particle. X goes to several millimeters of aluminum and then it stops, or aluminium. There we go, so that's going to be a beta particle, and Z goes all the way through till it hits some lead. That's going to be a gamma ray. So there we go. We're looking for beta, alpha, gamma. And that is option B. Question 40. The count rate measured when near a radioactive source drops from 542 counts per minute to 94 counts per minute in 12 hours. The background count remains constant at 30 counts per minute. What is the half-life of the source? Okay, so let's find our count due to the actual source. So 542 minus 30 is 512. That's what we start with. So at the start, and at the end we have 94 minus 30, which is 64. They're the counts due to the radioactive source itself. So let's just see what would happen. We've got half-lives and a count. Let's see, we've got no half-lives. We start with 512. Then we've got one half-life. That will go down to 256. Two half-lives, 128. Three half-lives, 64. There we go. So we can see it's taken 3 half-lives to go from 512 to 64. Now, 3 half-lives happens in 12 hours. Then 1 half-life is 12 divided by 3, which is 4 hours. So there we go, that's the end of the paper. Hopefully you found that useful and you enjoyed it. If you did, please feel free to like and subscribe. And either way, have a great day.